Thank you very much. Thanks for coming to our talk here. This is about very large-scale graphs, and particularly for working in manufacturing. My name is Paco Nathan. I lead a company called Darwin. We focus a lot on open source integration, especially for machine learning projects. And we've been making a lot of use out of Ray. So first off, I want to try to describe a bit about what we mean by graph, because in practice, graph has a lot of definitions, and perhaps the scope of what's being done by customers here is a little bit different. So I'll talk about a few things here. One is the notion of graph thinking. And we've got some other talks that go into this in much more detail, some other videos and whatnot. But it's a lot of the foundation of how we approach the business units and build out applications. And just also give a little bit of background as far as what current definition of knowledge graph might mean. It's been a very slippery definition over the past 20 years since it emerged out of Stanford and whatnot, 2001. And just some of how we got into this space, particularly by doing work with graph data science in open source. So graph thinking, the idea is that if you have a network view of your data, if you have linked data, by having a network view of it, it brings it closer to the people who are really the domain experts who can make sense of it. Networks are inherently complex. And there's a lot of problems with doing computation on networks if they get to a certain scale, certain types of complexity. So what we want to do is be able to take the relevant parts, bring it close to the people who can make sense of it, help them to acknowledge and work with the complexity, help them to identify emergent patterns, and then be able to make informed decisions off those patterns. Now, in the bottom right here, there's a small graph. And this is out of some of the larger talks, this is a medieval village. Pretend it's off in the Black Forest somewhere. There's 7 people. They each have some cottage industry. One of them works the wheat fields. The other one raises poultry. Another one runs a brewery. Another one runs a pub. But in the context of a small village, you definitely have the economic activity can be modeled by a graph, and it's very apparent. However, if you take that same data and represent it in a normalized form for a relational database, you get something like this. You'd end up with like 6 tables, and you've got your primary keys and your foreign keys. You've got your ERD diagram. But the thing is, it's just atomized to the point where if an expert in medieval villages looked at this data, they probably wouldn't make much sense out of it. And that's the problem, is that we have a lot of data in data lakes, and the people who have to do really complex things in finance, working with supply networks, working with very complicated sales deals, they're having to deal with this, and they can't really see the problem. But when we put it into graphs, they can. So I'll just link out here. Graph Thinking is an article that Jürgen, in the front row here, Jürgen Müller at BASF, he and I wrote this. There are some talks about it. Ben Lorica, who's the co-chair, Jen Webb and Ben Lorica did an interview about this last year on gradient flow. Now, the thing that's strange about graphs is I've been working in this field for a while, and if you'd listen to the industry analysts like Gartner, up until late 2020, there really wasn't a lot of credence given towards what was happening in graphs. Semantic web happened a long, long time ago, and graphs are inherently complex and can be inherently expensive. So the industry analysts had been kind of, saying not the best things about it. But then abruptly in February of 2021, Gartner did an about face. And they came out and they said, look, at this point, 50% of the calls that we get from enterprise about AI are about graph technologies. And even though we're only seeing 10% penetration in terms of data analytics that are using graphs in 2021, they project that by 2025, that will go up to 80% of all data analytics. So inherently, we're seeing a lot more of these kind of linked data cases and this kind of practice in industry. And down the bottom graph is where the real key is. So, one of the main points that Gartner made out of this in this report was that by exposing metadata and exposing the business rules of how you're using your data, this is where you really leverage a lot of the power of graph technologies. So if you're familiar with using spreadsheets, there is a dependency graph in every spreadsheet. And the vendors go to great lengths to hide that. It's very hard to ever see the dependency graph. But it has to be there. That's what does the calculations. If you're working in SQL with a relational database, you've got ERDs, you've got the query plan, which itself is a DAG, which is a graph. Graphs are very, very inherently important working with either Excel or SQL. But you don't usually see it. And the problem is that over time, this has taken the metadata and the business rules that we're working with in IT and swept it under the rug, tried to oversimplify it. And that is a problem. It leads to a lot of tech debt, and that's what we see in industry. So that's where we're getting a lot of uptick on graph usage, is the recognition of they have complex problems, they have tech debt that's been swept under the rug, they need to get the data in front of the people who can actually work with it as opposed to the IT priests on the data lake. So, the other talks go into much more detail, but there are a couple of models for this. They're actually really interesting to compare and contrast. There's the Cynefin framework that came out of IBM in the late 90s. If you've ever heard the Rumsfeld term of unknown unknowns, it came from Cynefin. And the idea is that as you have a business decision context, if it's simple, you have known knowns, and you can just apply rules. And if it gets more complicated, then you end up having data analytics and analysts to go out and advise the decision makers. But when it gets into a really complex kind of environment, like you see today with global operations, with supply chain, with pandemics, with economics, et cetera, instead, really, you have to focus more on probing the situation, sensing patterns, making informed decisions off of that. Probably some experimentation as well. And if you go over into cognitive psychology, there's a very, very similar set of patterns. There's this idea that as humans begin to learn a new topic, they usually start out with disconnected facts. And then as they become more and more familiar in the field, they start to chain those kinds of facts together into associations. As they get more and more familiar, they start to make more like decision tree kinds of models cognitively. But when people get to expert levels of understanding a domain, they break the rules. And instead of having decision tree structures, they have more graph-like cognitive structures. So we see a lot of parallels there, and I could go on at length about assembly numbers and things like that. But the idea is, if it's simple, you probably are using a spreadsheet. If it's complicated, you're probably using a data lake. If it's a really complex problem, you probably need a graph. And so, as far as a knowledge graph, this has been kind of slippery, but I'll make some general definitions here. When we talk about a graph, we talk about entities or nodes or vertices. These usually have some kind of unique name, like an RRI. They usually have some kind of attributes. Some of the attributes may be relations or edges or links, arcs that go out to other entities. Other kinds of attributes may be values. And in the more general case, any of the above may have probabilities associated with them. We often use controlled vocabularies of one form or another to try to overlay semantics on this in terms of having shared definitions of what these different parts mean and how they can be translated. And the bottom line is, if you've ever worked in any object-oriented programming language, you've seen all of this before under different names. That's really nothing new, but it is a bit more sophisticated in terms of how it's used. So some good resources here, friend Juan Sequeira and also Claudio Gutierrez. They had a great survey of the history in ACM last year. Iden Hogan and about 20 other authors have a really excellent paper from a couple of years ago that's a survey. And then the original paper was really Natasha Noé and Deborah McGinnis back at Stanford. And you can even go back in the 19th century and see Charles Sanders Peirce talking about knowledge graphs. There's a lot of emphasis now because there are things like graph neural networks. And I've been working in neural networks since about 1985. Probably the best survey paper that I would point to at this point is Inez Chami, graduated recently at Stanford. And she put together a really excellent survey paper, the first one. Michael Bronstein, of course, has led a lot of the geometric deep learning thinking that's come out of Twitter and whatnot. And definitely some other good links there. We work with Maciej Best at UTH Zurich. So this brings us up to the need to be able to apply these kinds of technologies for data science projects. And so a couple of years ago, myself and some of the others, there's different folks from our team here, we started putting together an abstraction layer in Python that would try to have integration paths between these different disparate technologies. And it's called KgLab. It's been out for, like I say, a couple of years. We've got a very active developer community. It has some other tangential open source projects that are popular as well. And the idea was to be able to have a kind of integration roadmap between, say, some of the more Pythonic or rather PyData types of approaches that are popular in data science, pandas and these sorts of things, but then be able to build out to how can we work with, say, for instance, probabilistic graphs? How can we work with semantic technologies, W3C standards? How can we run graph algorithms efficiently? How can we do visualizations, et cetera? And along the way, what we found were a couple of things. One is that the serialization formats that are used in graph technologies are usually fairly poor. I have a background, of course, working in Hadoop and then Spark and then Ray. And what we found is you're really talking about column stores when you represent the general case of graphs. So by moving to Parquet files, you can get a couple of orders of magnitude increase in efficiency in terms of serialization. And there's other benefits as well, but certainly as far as partitioning. So, you know, we started working with Parquet and we found that a lot of people like that. The other thing that we ran into, of course, is there's this great work that's come out of, well, Maryland, but now Santa Cruz, and I guess Brown as well, Lisa Couture and some of her grad students. It's called probabilistic soft logic. There is a general case that's called statistical relational learning. And some of these are very complex methods, like Markov networks. They're very computationally expensive. PSL has some really interesting properties because they use a hinge loss approach to calculating probabilities. It's a kind of conical optimization. It really bounds the problem. What it means is that you can have probabilistic rules that will go through the graph and assign probabilities on different nodes, different relations. But then you can also get a probabilistic measure of how consistent is the graph overall. And this is an important thing if you're doing, for instance, enterprise ETL. When you're bringing in a new data set, you can measure before and after of how consistent is this graph. And if the latest ETL batch job suddenly blows out your metrics, you know something's wrong. And then you can go and use the same thing as a lens to identify what are the parts that were just imported that actually don't really fit our descriptions. So probabilistic ways of doing data quality, I think, is with a semantic overlay is actually a really important way forward. So to sum that up, as we've been doing this over the past couple of years, graph data science was really interesting to our team and our friends, but there's several different areas, and unfortunately, they don't really talk with each other. They don't present at the same conferences typically, and if you go and use their GitHub projects, there's really no integration path. So there's really fantastic things you can do in probabilistic graphs, but it's not the same graphs as if you want to run a Cypher query. And it's not the same graphs if you want to run some sort of like NetworkX or cuGraph graph algorithm. Or if you want to drop down into like bulk synchronous processing and do procedural traversals like in GraphX. Also, not the same graph if you want to be doing visualizations. And also, graph neural networks are doing their own thing. So are the people over in W3C. So the premise was, how can we build integration paths? And how can we have mathematical transforms to go from one of these to another, do the calculations, and then do inverse transforms to populate the results back into the original graph source? And so that's a lot of what we've been doing. And as we were doing that, we had some folks from manufacturing contact us. So first off, some friends over at Siemens got in touch and said, hey, they want to use this. And then another friend at Bosch came in and said, hey, we're using this too. And then other friends at BASF came in and said, not only do we want to use this, we want to extend it. So let's see how far we can push this. You know, when you look in the graph space, there's been a lot of work in terms of social networks, in terms of advertising. These are kind of the popular cases that people talk about. There was really great work shown from ByteDance here yesterday. We've seen a lot of graph work in finance, but where we've been more focused is looking at verticals like manufacturing and closely aligned verticals like pharma. And they tend to have common problems. So this is really different from, say, what the tech giants are doing. And I got a really good measure of that by hosting Metadata Day, the couple of those that came out of LinkedIn a couple of years ago. Some of the problems that we see are being able to work with motifs, or if you will, subgraphs, and be able to handle these as a kind of unit of work or a data object, if you will. Of course, there's very high levels of complexity, but also a lot of uncertainty to manage. The problems that we find in data preparation are actually harder than the use cases downstream from them. So things like cycle detection and remediating cycles in use cases where they can't exist, disambiguation, similarity search, et cetera, those are really hard problems at scale. And ultimately, these kinds of applications are more interested in diving in, focusing on details of a problem spot and resolving it. They're much more interested in that, sort of zoom in and zoom out, than they are looking at aggregate count numbers. Okay, so it's a different kind of data science work. And so I just want to run through real quick of what a typical use case looks like coming out of manufacturing. In that space, when you talk about working on a job for a customer, you're often talking about bill of materials. A BOM is sort of a central data structure. So a customer has an order, and there's certain things that have to be filled out for that order. Maybe you've got 100 units that you have to ship, and you can get 50 of them out of one plant, and then another 20 out of another plant, another 20 out of someplace else. So you have to be able to fill the order probably from different sources. While you're doing that, you have to track where those sources were. If there's different product SKUs, maybe like, for instance, in discrete manufacturing, there will be maintenance schedules required. There's a lot of regulatory rules about this. If you're shipping somebody a multi-million-dollar turbine, that thing's going to need to be repaired. They need to know each and every part. So when a sale order goes out, you've got this bill of materials, and it will be thousands of nodes. And at a large manufacturer, you'll be seeing hundreds of thousands of these per month. So inherently, just looking at the sales data, you've got large graphs that are going into, pretty soon, hundreds of millions. If you start to put in the vendor networks, if you start to put in metadata that you have about your manufacturing process, like if you're in chemistry, there's really large chemical ontologies, material science, et cetera. And you start to look at other kinds of data, pretty soon you get into billions of nodes in a graph and maybe trillions of edges. So I just try to show that if you start out from customer orders, you've got a smallish graph-like thing, and then you start to lay on maybe some vendor data, and then let's also take a look. These companies are very interested in carbon footprint and how to have more sustainable sources for energy because they're very large energy users. So we start to track that as well, and then maybe we're looking at competitive intelligence and shipping manifests of what's going on, why do we lose a bid, who got it. Once you start to get this picture here, it becomes very valuable in a corporate setting, but it also becomes a very large graph. I want to point to some really excellent material for different use cases. Jürgen is here. Jürgen and Jonas there's a YouTube video about BASF, Stefan Lamparter and Thomas Hubauer from Siemens, another friend, Erlang Gonzalez, from Bosch, and in particular, I would really point to the top two. I think that Stefan Reiling, what he did with this use case at Novartis, really kind of illustrates some of the techniques that we use. Again, he's constructing a probabilistic graph out of a lot of scientific research. There's sort of a triangle of like molecules, genes, and diseases, and they can learn a lot from that. And in Novartis's case, it was hilarious because they came out with these predictions of drug discovery, and in Reiling's video, the biologist pushed back and said, "Hey, 80% of what you're showing us, we've already seen it before." And so he pushed back and said, "Well, what about the other 20%?" And the biologist was like, "Nope, let's go test it." So they're actually prioritizing their wet lab research now based off of graph analysis. There's a lot of hurdles. I probably need to move on in time, but one of the big things is that, this is complex work. No doubt about it. This is a really kind of complex approach to AI. It does lend towards more of like the neurosymbolic kinds of cases because it tends to blend the numeric with the symbolic. There's a lot of vendors in this space. There are actually about 50 graph database vendors, but they're all very focused on the idea of having like database commits and really old school transactional sort of notions that don't fit horizontal scale out of extremely large graphs. So we've identified some problem areas. One is that there's these disparate camps. There's the people doing like W3C, and then there's people doing labeled property graphs. And there's really nobody who was out there where you could query the same data with both of those approaches. There's a lot of emphasis on database transactions, but in enterprise, they already have a lot of databases. There's really great vendors in this space. Graphicstry is one we work with closely for visualization. But the thing is that like deep learning and visualization are downstream from the data prep. And the data prep is the computationally hard part. That's where you're working in billions of elements to be able to, like, for instance, get rid of cycles. The other thing, too, is that in this space, enterprise licensing is no joke. You're going to, with some of these vendors, they really do kind of push you toward scale up instead of scale out. So you end up with really expensive cloud instances and paying a lot for them, and then paying as much or more in terms of enterprise licensing. So it's a very costly thing, even though most of them also have some serious performance bottlenecks. So, you know, we went after this. We definitely have been working on integration paths already. And I think one of the better papers to really illustrate some of the compare and contrast between the different camps, the path query paper that came out of Google recently, I think is a really good introduction to the different query languages like Sparkle and Cypher, and then what they're doing. And in fact, how Google has introduced constraints on their language which make it more performant in distributed systems. Oh yeah, and here's like a list. I curate a list for the Knowledge Graph conference. Here's a list of 50 vendors we've identified so far and open source projects and what some of their attributes are. If there's anything that needs to be added, just email us, we'll add to it. But it's kind of like, in a nutshell, who are the vendors in this space. Yeah, again, the hard problems that we're dealing with are upstream. They have to do with data preparation. And there are some times when you really need to dive into the graph theory. Like, if you just take the raw data and start to visualize it, you're probably not going to get something that has a whole lot of insights. You may need to do some transforms on the graphs. And that's where you can get into some types of transformations that, if you don't have the math, it's good to get it. Where am I? Okay. So we started looking around to see really, you know, what's the North Star? What are the other projects that might work really well here? And certainly Ant Financial has presented here. Ant Financial and Alibaba have been working on GeoBase, and that's very much in category of the kind of scale and performance and a lot of the attributes we're really interested in. There's another project called Nebula Graph by BASF, also out of China, and Grasper from Hong Kong University. I think also what, you know, ByteGap that they were showing yesterday from ByteDance. All of these are really in category for a lot of the scale objectives and performance and cost, et cetera. On the downside, though, they tend to be more ad hoc implementations. They don't really, you know, enable something like a Sparkle query or a Cypher query. There's a lot of things that use cases already demand that just they aren't implemented. And there are security concerns and IP concerns. Our firm does work with US federal agencies, and as far as open source projects, they do tend to prefer US-led organizations. So we moved ahead on working toward horizontal scale out for trillion node graphs that could have a lot of richness, really overcoming the performance need that you see at about 100 million. And in particular, it's the load and store, the serialization operations are the ones that are just really killer if you're using something like Neo4j. Also, a lot of support for more advanced graph algorithm work, not just queries. A lot of need for eventual consistency in terms of how we manage data, multi-tenancy, on and on. So how can Ray help support this? We've been struggling with this idea for a while. When we were doing KgLab, we were thinking about how can we take and distribute it and still use the graph query parser, still use the algebra for query optimization, but then distribute the data. And there are other things along the way that really touch on distributed systems, and we would love to use. Frankly, though, the first part is so far where Ray has helped. There are two critical paths. So if you're doing Sparkle queries, if you're working with RDF and OWL and all that, the real critical path in distributed operations is to have the triple iterators. Really, tools like RDFlib or Janet or others, they take care of the front part of it. It's the iterators being fast, that's the problem. And with data sets in Ray, of course, we have iterators for that. That's great. Cypher, labeled property graphs, it's a bit more complex. You have to be able to do some parallel enumeration across unbounded paths, so all shortest path Again, we're using Ray and Dask for that. There's a few other likes we would have. Let me move forward. What we've done is to build out something that has partitions written in C++ using HPC libraries. And then we manage the partitions using rings of Ray actors per named graph. And we have a multi-tenant setup to manage multi-tenancy for different named graphs in memory at the same time. We're using projects like Morph and PSL and RDF-lib for a lot of the needs on graph, also OpenCipher, and doing the sparse matrix work right now in Dask. And then at a lower level, we're making a lot of use out of Parquet and Arrow. We have a pulsar message queue for all destructive operations coming in. And then we use Bookkeeper as a distributed ledger for all the checkpoints to keep track of whatever's serialized. What this means is we can reconstruct any particular graph at any point in time by taking a pulsar topic and then restoring a checkpoint and replaying the queue from that point. And of course, based on security, we have to have API access for this. So, you know, we've got Nginx and Keycloak for the ingress controller, and we've got Fast API and Pedantic for the API. But we're using Ray on Kubernetes and making a lot of use out of placement groups because of the memory requirements. That's been the hard part that we really struggled with, and also just getting up to speed, Ray on Kubernetes, but that's been a lot of fun work. And right now, Wes is working on, we're coming out with a version of this that just does a mini-cube deployment, so it accelerates our local development. As far as what we'd like to see in Ray, what would help, there's a link on the first line to how to get around the restrictions of Python with Ray. One of the problems is that if you have a class, an actor class, and it's calling out to Python, Ray changes the arguments, the parameters that are going in. So you end up having to refactor your code, so you just have no arguments on the initializer, and then have like a setup pattern immediately following that. So we've got a GitHub repo that shows how to do this. But basically, C++ isn't quite playing nice with other C++. It would be great to have a tighter loop on the vulnerability scans for the Docker Hub images for Ray. We're having to use the Ray published images, but then we had to reverse engineer the build of those images because we ran into security issues. And so having better scripts for custom build of Ray on Kubernetes would really help out. And we've already got a GitHub repo that's public that shows how to do some of this. That might be fun to work back in. It would be nice if we had Ray-based replacement for really high-performance hash maps, where we could do fast scans and LRU memory spills. And this is pretty much what ByteDance was talking about in terms of the tiered persistence. Pretty much the same thing. And BSP support would be great. We're looking for collaboration. And so at this point, I'll ask, if this project were made open source, how many people would be interested in using something like this? 1, 2, 3. About more than half the room. OK, that's for the corporate benefactors. They need to know this. And for that, what are some hotspots? Like, how many of those of you who would like to use it, probabilistic graphs, is that an interesting thing? Who would like to use probabilistic graphs in this kind of context? That's also really great. Thank you. What about the other thing we were wondering was about partitioning. I guess another question we'd have. So one thing I haven't mentioned is that we use an approach called shadow nodes. So in some approaches of implementing graphs, it's more centered on the node, on the vertex. We center on the edges. And so we can do fast iterations through the edges, and we have enough metadata for the destination nodes, even if they exist on another partition. And so that means that we're not as sensitive to needs to repartition, rebalance. We can do that, but offline. But I'm just curious about partitioning, how much of a problem that is. Maybe people foresee issues there. For supernodes, yeah. We were just talking about it, so let's talk more. We have some ideas. OK, real quick, there is a LinkedIn group for graph data science, and we've got over 500 people now if you want to join us. And these slides will be online. And also, if you want to get a hold of me, I'm here. Thank you very much.
Thank you, Paco. We have time for 1 or 2 questions, and I can bring the mic to you. Are there any questions?
And I will also ask if maybe Jürgen and I can both kind of field the questions.
All right. If not, feel free to come up and talk. Oh, we do have one question.
Cool.
Thank you so much for introducing such cutting-edge technology and with versatile use case. So I have a question regarding, I have two questions actually. The first one is how generalizable do you think is the graph learning algorithm across customers? Does each customer need babysitting for customer tuning, or is it generalizable? The second, oh, go ahead please.
Yeah. Oh, okay, yeah. Well, for that question, I mean, so there are a number of different machine learning approaches that can be applied. Definitely with graph neural networks, there's a lot in terms of link prediction and basically looking at the data and saying, okay, I think something's missing here. Somebody should really review because we think there's an important part that, like a link that should be there but isn't. The other thing, though, is this idea of motif mining. So if you take the neural networks, sort of turn them backwards and turn it into supervised learning on the patterns, then you can basically bring out what are the patterns that seem to show up a lot, and of these, what are important. And so this is another kind of machine learning, really, to understand the shape of the data and understand what, like in a data warehouse, you would talk about data objects. So how are those emergent? Because that can be really complex and also non-intuitive. Finance departments may not understand the pattern of shipments between warehouses, but they can see it once you've got the data. So I think that there's a lot of room ahead for generalizing, but also having kind of a feedback loop, a human-in-the-loop aspect of the visualization in tandem with iterations on the machine learning, if that makes sense.
Yes, that's super helpful. Sure. The second question is, because I work a little bit in manufacturing and customers, and one of the problems we find is that with vendor network you mentioned, it's a great use case for graph, Absolutely. But the problem we find is that if we learn the graph and we do a what-if analysis on top of that, we find if we incorporate the first tier vendors, it's okay. If you go to the second tier vendors, it's like you're incorporating the world and the signals get extremely noisy. So what's your take on that? Thank you.
Great question. Okay. Yes, we were talking about this over lunch. Well, definitely. You can get into situations of it being very noisy. This is where we believe that probabilistic graphs are especially useful, is because where can we point toward evidence to try to weed out the noise or filter it or reshape it in some way to be able to find these kind of pathways that are most interesting or most useful. And so by having probabilistic elements introduced throughout the graph and then being able to do, again, something like PSL, we can add a layer of analysis that just isn't there in queries. And in my experience in data science, this kind of filtering is extremely important. So I want to incorporate this into graph data science practice. Does that help?